The next Higgs video. It's B tagging HERA, Higgs Boson Particle Decay Signal Bottom Quarks CERN. It was done on September 29th and today's November 15th, 2012. The keyword search is from the HERA 1, HERA 6, Higgs Mass Boson Particle videos. So basically these are all the different keywords that came up in those videos that I didn't understand, so I'm doing the research on them to see what they mean. So September 19th, I did B tagging. Many quotes and data come up from Wiki. B tagging is an example of a jet flavor tagging method used in modern high-energy particle physics experiments. It is the identification or tagging of jets originating from bottom quarks or B quarks, hence the name. So I googled the keywords Higgs boson decay into bottom quarks to see what comes up. And gluon fusion, if the collided particles are hadrons such as the proton or antiproton, as is the case in the LHC and tevatron, then it's most likely that two of the gluons binding the hadron together collide. The easiest way to produce a Higgs particle is if the two gluons combine to form a loop of virtual quarks. Since the coupling of particles to the Higgs boson is proportional to their mass, this process is more likely for heavy particles. In practice, it is enough to consider the contributions of virtual top and bottom quarks, the heaviest quarks. This process is the dominant contribution at the LHC and tevatron, being about 10 times more likely than any other processes. So these are the Venn diagrams for the Higgs production. We get the gluon fusion, and then we get the Higgs strion, top fusion, and vector boson fusion. So a Higgs particle can be produced in a particle collider by taking two particles and smashing them together at very high energies. The exact process depends on the details of the particles used and the energy at which they are collided. But in any case, the probability of producing a Higgs boson in any collision is always expected to be very small, with only one Higgs boson being produced per 10 billion collisions. That's crazy. You have to do 10 billion collisions to find one Higgs boson? Wow, that's a lot of work. So Higgs strion, if an elementary fermion collides with an antifermion, example a quark with an antiquark or an electron with a positron, the two can merge to form a virtual W or Z boson, which if it carries sufficient energy can then emit a Higgs boson. This process was the dominant production mode at the LEP, where an electron and a positron collided to form a virtual Z boson, and it was the second largest contribution for Higgs production at the tevatron. At the LHC, this process is only the third largest because the LHC collides protons with protons, making a quark-antiquark collision less likely than at the tevatron. The weak boson fusion, another possibility when two antifermions collide, is that the two exchange a virtual W or Z boson, which emits a Higgs boson. The colliding fermions do not need to be the same type. So, for example, an up quark may exchange a Z boson with an anti-down quark. This process is the second most important for the production of Higgs particles at the LHC and LEP. Top fusion. The final process that is commonly considered is by far the least likely by 2 orders of magnitude. This process involves two colliding gluons, which each decay into a heavy quark-antiquark pair. A quark and antiquark from each pair can then combine to form a Higgs particle. So here's a diagram I found with decay width in GeV and Higgs mass in GeV. Okay. It says the standard model prediction for the decay width of the Higgs particle depends on the value of its mass. This diagram says branching ratio and Higgs mass in GeV. And then it's got TT, BB, CC, some other symbols, II, UU, GG, YY, ZY, WW, and ZZ. So they're all color coded, and then there it shows you the graph where they go. So the standard model prediction for the branching ratios of the different decay modes of the Higgs particle depends on the value of its mass. For a Higgs boson with a mass of 126 GeV c squared, the SM predicts a mean lifetime of about 1.6 times 10 to the minus 22 seconds. So it doesn't last very long. And what I'm trying to do is find a way to make it last longer. One way that the Higgs can decay is by splitting into a fermion-antifermion pair. As general rule, the Higgs is more likely to decay into heavy fermions than light fermions because the mass of fermion is proportional to the strength of its interaction with the Higgs. By this logic, the most common decay should be into a top-anti-top quark pair. However, such a decay is only possible if the Higgs is heavier than 346 GeV(c²), twice the mass of the top quark. For a Higgs mass of 126 GeV(c²), the SM predicts that the most common decay is into a bottom-anti-bottom quark pair, which happens 56.1% of the time. The second most common fermion decay at that mass is a anti-tau pair, which happens only about 6% of the time. Another possibility is for the Higgs to split into a pair of massive gauge bosons. The most likely possibility is for the Higgs to decay into a pair of W bosons, the light blue line in the plot, which happens about 23.1% of the time for a Higgs boson with a mass of 126 GeV(c²). The W bosons can subsequently decay either into a quark and an antiquark or into a charged lepton and a neutrino. However, the decays of W bosons into quarks are difficult to distinguish from the background, and the decays into leptons cannot be fully reconstructed because neutrinos are impossible to detect in particle collision experiments. A cleaner signal is given by decay into a pair of Z bosons, which happens about 2.9% of the time for a Higgs with a mass of 126 GeV(c²). If each of the bosons subsequently decays into a pair of easy-to-detect charged leptons, electrons, or muons. Decay into massless gauge bosons, i.e. gluons or photons, is also possible, but requires intermediate loop of virtual heavy quarks, top or bottom, or massive gauge bosons. The most common such process is the decay into a pair of gluons through a loop of virtual heavy quarks. This process, which is the reverse of the gluon fusion process mentioned above, happens approximately 8.5% of the time for a Higgs boson with a mass of 126 GeV(c²). Much rarer is the decay into the pair of photons mediated by a loop of W bosons or heavy quarks, which happens only twice for every 1,000 decays. However, this process is very relevant for experimental searches for the Higgs boson, because the energy and momentum of the photons can be measured very precisely, giving an accurate reconstruction of the mass of the decaying particle. To search for the Higgs boson, two beams of particles are accelerated to very high energies and aim to collide inside a particle detector. So September 29th, we're going to explore particle detectors in the next video. Thank you for watching.